and welcome to the Chapter 7 lecture video. Here we're going to talk about the interesting topic of planets around other stars, because recent discoveries have shown that many stars have planets around them. And we're going to learn, what are these planets like? Are they like the planets that we've been learning about in the last two chapters, like the terrestrial and Jovian planets? Well, let's see. All right, so our goals in this chapter, and specifically section 7.1, are to understand why is it so challenging to learn about extrasolar planets? Why did we not learn about them until 1995 with the first confirmed discovery? How can a star's motion reveal the presence of planets, right? Important technique. And how can changes in a star's brightness reveal the presence of planets? Okay, so these are going to be two of the real techniques we're going to talk about that astronomers use. All right, well, let's get into it. All right, so here we have an actual direct image taken of planets. These little infrared dots, by the way, that's what this image, the spectrum of this image, were directly resolved with a special technique where the overwhelming light of the sun is canceled out and the much, much fainter light of the planets can actually be picked up with a special type of photographic technique. All right. So this is not the normal way we detect extrasolar planets, right? This is possible in certain cases for certain nearby stars, but they have to be aligned just right. The conditions have to be just right. So most of the time, astronomers use other ways of finding extrasolar planets, although it is pretty cool to get a direct image like this. All right, so let's talk about brightness and distance. So a sun-like star is about 1,000,000,000 times brighter than the light reflected from its planets. All right, so that really gives you some perspective on that last image. In order to get those little dots, those reddish yellow dots that were a few pixels across, they had to cancel out the light of a central bright spot that was a billion times brighter. Imagine like trying to take a picture of a light bulb that's 1,000,000,000 times brighter of the little specks of dust that you're trying to resolve around that light bulb. Wow, right? That's a tricky thing to do. Planets are also close to their stars relative to the distance from us, right? So again, another just drastic comparison. This is like being in San Francisco and trying to see a pinhead 15 meters from a grapefruit in Washington, D.C. That is literally the actual angular scale we're talking about. And then imagine that the grapefruit is 1,000,000,000 times brighter than the pinhead. No wonder there's not many direct images of extrasolar planets, otherwise known as exoplanets, right? It's amazing we have any. All right, so how do we learn that other stars are suns? Well, we've talked about this idea that ancient astronomers didn't realize how far away they were because the whole parallax conundrum, but then finally we realized they're so far away. So let's summarize. Ancient observers did not think stars were like the sun because the sun is so much brighter, right? The stars had to be different. They couldn't be that far away and that faint. All right. In the mid 1600s, Christian Huygens used holes drilled in a brass plate to estimate the angular size of stars. His results show that if stars were like the sun, they must be at a great distance, consistent with the lack of observed parallax. Right. So this was a key point where astronomers really began to seriously think from the mid 1600s on that they actually were perhaps other sun-like objects, but they were just that far away. And that, of course, led to the eventual discovery of true parallax that was just a few arc seconds across, or really less than 1 arc second of parallax, the maximum case of the most nearby stars like Alpha Centauri. All right, but that wouldn't come until over a century after Huygens' kind of confirmation that perhaps they were really that far away. Okay, so how can a star's motion reveal the presence of planets, right? So now that we realize that stars are so incredibly far away, light years away, and that they're just as bright or brighter than our sun, but they appear faint, then what can we do? How can we measure anything about them? How can we determine that if they have other planets orbiting them? Well, one of the key ways is wobble. All right, so let's consider our own solar system, considering Jupiter and the sun. Well, it turns out that when you have a two-body system, like just the sun and Jupiter in consideration, the center of mass, the balance point between the sun and Jupiter, is not at the center of the sun, right? We think of the center of the solar system being the center of the sun, but it's not really. The balance point would be somewhere else, actually near the surface of the sun. All right. Now, of course, that's a tiny fraction of the distance. This is not to scale at all. But it is true that the center of mass is near the surface of the sun. That means that the sun will actually wobble. It will spin about a point that is near its surface. A absolutely measurable wobble. All right. Very obvious if, from a distance relatively close like we are to our own sun, we can definitely see the sun wobbling about a point. And of course, the sun's wobble is actually not just caused by Jupiter, but caused by a combination of all the planets. So it's a very complicated wobble over time. Okay? So that happens for all stars. They all wobble. Well, at least those that have planets, which are the vast majority as far as we know. So that means we should be able to measure that wobble, right? Well, that's the thing. Are we going to measure it directly? Like, take pictures of the wobble and actually see it move side to side? Well, unlikely, right? Considering that the whole parallax effect is only an arc second, how much would that wobble be? I mean, it would be a millionth of an arc second of actual motion. We think about the diameter of the sun compared to the distances and our orbital distance from the sun, right? It'd be very, very tiny. So instead, we're going to indirectly measure that wobble. All right. And as far as direct could also involve, actually taking pictures of the planets like we saw before, but we could even take direct pictures of the wobble. But that's not what we do. Instead, we reveal properties of those orbiting planets. We're going to use something called the Doppler effect. Okay? So we're going to look at that gravitational tug, at that actual wobble. But instead of maybe looking at it side by side, we're curious because if you think about it, the sun's also going to be over here at some point and over here at some point. But let's say that our line of sight, right? Here's our eye. Our line of sight is this way. And so we're curious this way. We're curious about how the sun is going to wobble back and forth. Because that back and forth motion, not the side to side motion, but that back and forth motion is going to create an effect in the light. It's actually going to change the wavelength of the light in the same way that the wavelength of sound is changed by a source of sound that is moving towards you or away from you. Think about the siren of an ambulance as it passes you. When it's passing you, it's very high pitched, and as soon as it passes, it's low pitched. It might sound a little something like, right? That is the Doppler effect. And the same thing happens of light. When something's moving towards you, it's higher frequency, shorter wavelength. And when it's moving away from you, it's going to be that lower frequency, longer wavelength. Okay? And that's called the red shift and blue shift. All right? So the sun and Jupiter orbit around their common center of mass. Okay? The sun therefore wobbles around that center. Okay? Here's the complicated wobble from all of the planets. All right? And this is the kind of thing that astronomers are going to have to deal with and are dealing with for planets around other stars that have more than one planet, which are most other stars. Okay? So, but it's around our own sun. It's quite fascinating, and this is again is a combination of all the planets. Because Earth tugs on the sun, obviously much less than the big planets like Jupiter and Venus and so on. No, I said Venus, I meant Saturn. But they all tug a little bit, and the overall effect is this: over many years, the sun is wobbling around. Okay, all right. These variations are tiny. They're very difficult to measure. All right. So maybe a thousandth of an arc second. All right. There's spacecraft that are helping us measure those actual physical wobbles, but instead of looking for that physical motion of the actual diameter of a distant star moving back and forth, we're going to look at that Doppler effect. That's that analogy to sound that I made before with the siren, because when a star is moving towards us, the starlight is red shifted. Okay, because that's a longer wavelength. All right. Excuse me, that's when it's moving away from us. I said it backwards. Okay, so when the star is moving away from us, that's the lower pitch if we're making an analogy to sound, and that's the longer wavelength. That's the red shift. When something's moving towards us, it's blue shifted. All right. So red shifted is away, and blue shifted is towards. So any wobbling star is going to go through both. As the planet tugs on it, the unseen planet tugs on that star, the effect can be measured because the wobble will be there, and that wobble will correspond to a particular mass at a particular diameter, right? We can start to work out through mathematics what is that planet, that mystery planet that could create such a wobble. So measuring a star's Doppler shift can tell us its motion towards and away from us. The current techniques are remarkable. We can measure wobbles as small as 1 meter per second. All right, because the reason that this type of technique can be so precise is because we're looking for tiny wavelength changes. Well, we can measure wavelengths really well. We can take light and shine it through a prism or use something called a diffraction grating, which is basically splitting light up into its constituent wavelengths, and look for tiny, tiny variations in wavelength in a way that actual physical arc seconds could never be measured as accurately, because we're not limited by pixels in a camera, but instead by just the accuracy of the prism and the splitting of the light, which is something that can be built to much greater precision. So when we do that, when we measure the velocities, we get profiles like this. So this would be the velocity of a star towards and away from us. And this, in this case, fairly large, maxing out at about 50 meters per second towards us and negative 50 meters per second, or 50 meters per second away from us. And this would be over a duration of many days, okay? And this would show us the revolution of a planet. Because when the star is moving away from us here, well, what does that correspond to? That corresponds to a planet that's on the backside of that star and tugging the star away from us. On the other hand, when the star is moving towards us, that means the planet is between us and the star and is pulling the star towards us. So that means that this time, about 2 days, is the time it takes the planet to go from an orientation exactly in front of the star relative to us to exactly behind the star. So that means the total time is a 4-day orbital period. All right. Now this is an actual star that's wobbling. This is 51 Pegasi. All right. And this Doppler shift corresponds to a planet. It is evidence of a planet. It's the measurement technique. This is how scientists find exoplanets. This is how the first exoplanets were discovered. This is still one of the primary techniques. And yeah, it's indirect, but there's nothing else to explain that wobble. And this nice sinusoidal behavior is clear evidence that something is orbiting that star, something that's faint and small. And do remember that we have confirmed with direct photos some of these planets, right? This is really happening. This is evidence of planets, even if it does seem extra, indirect and just a little wobble. It is really telling us something. Now, there is something to notice here. 4 days is a pretty tight orbital period. This short period means that the planet has an incredibly short distance. All right, this was it. This was the first one they discovered. This was the first exoplanet. All right, it was around a sun-like star, and it was discovered in 1995. Now, okay, that's fine and all. That's great that we discovered a planet around another star, and it was a sun-like star. So nothing too exotic, something we can relate to. All right. But 4 days? I mean, Mercury has a pretty short orbit, right? But it's still 90 days, right? So that's certainly not 4 days. 4 days is a crazy short orbital period. I mean, that's hard to believe. Is that right? Or, is that something else going on? Well, it actually turns out that many solar systems do have these very, very close planets. These planets that are so close to their stars that it's very unlike our own solar system. All right. And it's actually helped us rethink about how solar systems are formed and what a typical solar system may look like. All right. So this planet around 51 Pegasi, in addition to having an incredibly tight proximity to its star and a very short orbital period, has a mass like Jupiter's. Wait a second. So not only is this like Mercury, but much closer, it's like giant Mercury much closer. And also, if it's that giant, it can't be like Mercury. It's got to be a gas giant. So that means that this type of planet is called a hot Jupiter. All right? And a hot Jupiter turns out to be a type of planet that we see around other stars. Okay? So, another way that we can measure and astronomers measure planets around other stars is through a brightness drop. Because when the planet is in between us and that star, it must be blocking some of the light. And the amount of the light that's blocked is not that large, because if you think about the diameter of the star and so on, it's not really, a significant size. I mean, if we were to measure the transit of Venus as it crosses in front of the star, it's just a little tiny black dot that's covering up the star. But it would be slightly reducing the brightness. And that's what we measure. We can measure from Earth for other stars. We can measure a reduction in brightness. And look, it can be, as much as 1.5% in very dramatic cases of giant planets passing in front of relatively small stars. But more often than not, it's a tiny fraction of 1%, right? So it's going to be, a tenth of 1% or even a hundredth of 1% reduction in brightness. All right. And we call it a transit because it's transiting in front of the star. It's going in front of the star. All right. And by the way, we can also look at when the planet is eclipsed, when it passes behind the star. And the two bits of data, the transit part and the eclipsing part together, can tell us something about the planet. It can tell us about how reflective the planet is, because the planet isn't just black. It's not just, a black hole in the sense of, it does reflect some light. And so when it is behind the star, the overall brightness of that solar system is reduced. Okay? So an eclipse is also sometimes seen when the planet passes behind the star as a change. And that the two bits of data together can really help tell us about perhaps the atmospheric qualities of that planet and all kinds of interesting facts. All right? Now, to get a perfect amount of transit data, you have to have no orbital tilt. So in other words, we have to be observing the star and its solar system, its ecliptic plane, just like all of our planets, orbit in a plane around our sun. We have to be observing it right edge on, right, in order to get perfect transit data. And that's also true of the Doppler effect. We want to have it right edge on to get that perfect Doppler effect of the star moving towards us and away from us. And can we be sure that it is edge on? No. Lots of times these are upper or lower limits of data, right? Because we're not quite sure what's going on. We can, through modeling and comparing, because we can do transit and the Doppler effect for the same planet and the same star, we can start to really work together on this information and, and come up with these complicated models and complicated comparisons between the data to tell us what perhaps is the axial tilt, right? It's amazing science. So Kepler, by the way, is a space-based telescope like the Hubble telescope that is specialized to look at exoplanets. All right, it was launched in 2008, and the type of measurement it makes is all about those brightness variations. So instead of looking at the Doppler effect, which can be measured fairly easily from surface observatories, it's looking at those brightness variations and the transiting planets. All right, it is designed to measure a 0.008% decline in brightness. All right, so it gets really good at measuring Earth mass planets eclipsing sun-like stars. It was specialized for that purpose, and it has found lots of Earth-like planets, which is pretty darn cool, right? It has found over 4,000 planets, all right, 2,335 confirmed planets as of 2017. Not bad, all right? Some other techniques include gravitational lensing, which is the idea that due to Einstein's general relativity, or theory of general relativity, mass bends light, and we can see that bending, that slight variation due to the mass of the planets. We can also look at features in dust disks, gaps, waves, and ripples that suggest that in these early solar systems, we can actually see evidence of the planets pushing around the thick molecular cloud that's left from the star formation. All right? So hopefully we've made it clear that it's very challenging to learn about extrasolar planets because they're so dim compared to the bright stars, and that we can use two primary techniques, the Doppler shift and the transiting planet method, to determine if extrasolar planets are out there and what they may be like. All right. So now we're going to move on to the findings, because as you saw, right, there's been a lot of confirmed planets, right? Astronomers have been busy since 1995, and we found out a lot of interesting trends about planets around other stars. All right. So let's talk about that to wrap up this lecture. Okay. All right. So the nature of planets around other stars. What do we know about them? All right. So here's a cool graph showing some data that's been collected about extrasolar planets, and in comparison we have well-known planets in our own solar system. So let's take a look here. On the vertical axis we have orbital eccentricity, and on the horizontal axis we have average orbital distance. So right away we can see that in our solar system all of the planets have fairly low orbital eccentricity. All right, so that means that their orbits are fairly circular. We can see that there are a lot of planets that are distant, that are distances from other stars somewhere between Venus's and Jupiter's orbits that have highly eccentric orbits. All right, so that's something we don't have in our own solar system, right? But our solar system may not be entirely typical, right? It's, maybe not entirely unusual, but obviously there are a lot of solar systems out there, planets and other stars that have much more eccentric orbits. We're talking, about very, very stretched out ellipses, because if you recall, eccentricity is a term that refers to how stretched out an orbit is. So a circle would be very low eccentricity, and a really stretched out ellipse like that would be high eccentricity. So high E for eccentricity. Okay? So that's something right away that is different of the overall trend and fascinating. Okay? All right? So what are the measurable properties? Well, it turns out through combinations of transit data and Doppler data and the laws of physics that we know, we can determine a lot of information about these planets. It's really remarkable. We can determine their orbital period, their distance, their shape of the orbit, that is, how eccentric it is. We can determine the planet's mass, its size and density, and even its atmospheric properties, as I mentioned, because we can compare the transit data with the eclipsing data. All right? So here are just some examples of how we might parse out all those amazing facts about these extrasolar planets. Well, we can look at Doppler shift and we can see if it has a nice symmetric wave like that, a sine wave, that's telling us low eccentricity. Whereas if we have a wave that looks like this, right, that isn't sinusoidal, but instead is very asymmetric, still repeating, then that tells us that this is high eccentricity, okay? And then just looking at the peaks of the Doppler shift tells us about how the actual period and about how much force there is that's pulling on the planet. So then we can combine that and find out, what maybe is the mass of the planet. Okay, so we can measure an exact mass for a planet without knowing the tilt of its orbit, or we cannot, because the Doppler shift tells us only the velocity towards or away from us, right? So it's only telling us a component. So unless we're sure what the tilt of that orbit is, then that's one big caveat, is we're making an estimate of the mass, okay? So the Doppler data gives us a lower limit on masses, inherently a lower limit, right? Because we might be missing some of the mass, because we might be missing some of the pull, because some of the pull might be up and down, right, rather than towards and away from us. And we can't measure that with the Doppler effect, because the Doppler effect, is a very precise measurement. They can measure velocities as low as a meter per second for these distant stars, is limited to motion towards and away from us. It's very important. Okay? So suppose you found a star with the same mass as the sun moving back and forth at a period of 16 months. What could you conclude? All right? 16 months. What does that mean? Think about Kepler's law, right? That means that it has to have an orbit greater than 1 AU. Because if the sun has a mass equal to, or the star has a mass equal to our sun, then a planet that is orbiting with a period of 12 months would be exactly 1 AU. And since 16 is greater than 12, then the planet must be further than 1 astronomical unit. Okay, that's Kepler's law at play there. Now, if it was a mass other than a mass equal to our sun, then we have to do some other calculations. Okay. Furthermore, when we look at transit data, right, this is a wonderful example, right? Like we get this really messy looking data, but as scientists look for it and they filter that data and they match it to their models, they can see that these particular drops can correspond to a single planet transiting or maybe multiple planets transiting at the same time. And when they fit it all together, they find out that in this particular system, Kepler 11 is the name of the system, there's 6 planets. Right? And they're able to work this out from the transit data. So transit data can be actually incredibly valuable for finding multiple planets. Okay? So we can then use the mass determined using the Doppler technique and then size combined from the transit technique to calculate density. So stop and appreciate that. The two techniques together, the Doppler defined the mass because it is very well suited using Kepler's third law, or often referred to as Newton's synthesis of Kepler's third law. So we can calculate the mass that way. And then the transit data, that drop in brightness can tell us the size of the planet because the size of the star is known based on models that we have from the Hertzsprung-Russell diagram, basically the whole kind of the big periodic table equivalent of astronomy, something we'll get into more in later chapters. But the point is that we have all these models and this background knowledge, so we can get mass. Here, let's put blocks on everything. Mass from Doppler, okay, and we can get size from transit, and together that gives us density. And that's amazing, because once we have density, we can say it's a gas planet, okay, because if it's low density, it's got to be a gas planet. If it's high density, then that means it's rock and metal, and it's a terrestrial planet, okay? That's how we can say that a really big, massive planet, that, you know, that hot Jupiter I mentioned, is in fact a gas giant, because the density tells us it must be, okay? So notice how these techniques combine together. This is so cool, right? Using these two techniques together to get density, okay? Furthermore, we can look at the spectrum, right? So the change in spectrum during a transit tells us the composition of the atmosphere, right? So we can look for particular gases in the atmosphere, things like ozone, right? Things like oxygen, nitrogen. It's amazing, okay? All right, so measuring the change in the infrared brightness during an eclipse enables us to map a planet's surface temperature. Okay, so we can even get an idea about how hot this planet is. What is its surface temperature? Okay, really neat stuff, right? So how do extrasolar planets compare with planets in our solar system? So I've already established that there's definitely a more eccentric orbits out there in the average solar system than we have in our solar system. But what other differences might we find? Okay, so most of the detected planets have orbits smaller than Jupiter's, okay? Now that might just be a bias of our techniques, okay? Because it's going to be hard to find planets with orbits larger than Jupiter because the orbital period is so long. If we look at the orbital period, for example, of Uranus and Neptune, we're talking over 100 Earth years. Think about how difficult it would be for an astronomer to measure that. If you're waiting for a transit, you'd have to wait 100 years. Astronomers don't just sit around for 100 years, right? That means you have to get lucky. You'd have generations of astronomers before someone happens to get lucky to catch a transit of a planet that has an orbital period that long, okay? So that really is a huge thing to consider, that there's a bias for finding planets that are closer to those other stars. So most astronomers assume that many of these systems that we've discovered that have 5 or 6 planets that are within an orbit inside of Jupiter, they probably have a few more planets in orbits greater than Jupiter that we just haven't measured yet. Okay, so planets at greater distances are harder to detect with the Doppler technique, and much harder with the transit technique as well. Okay, so good luck combining those techniques together to get density. All right, so orbits of some extrasolar planets are much more elongated. They have a greater eccentricity. Okay, we mentioned that. That was this data here, all the high eccentricity that are fairly close in. By the way, we do have some pretty highly eccentric orbiting bodies in our own solar system, but they're all the really distant ones, like Pluto and other Kuiper Belt objects, right? That's where you're going to see eccentricities as high as these planets here that have been measured, okay? Furthermore, what about size, okay? So most of the planets detected by Kepler have lower masses than Jupiter. These percentages will certainly go up as we get better at discovering planets with longer periods, okay? So that's the thing, is we're probably not finding those distant gas giants. So we're finding a lot of Earth-sized planets, okay? So pretty common, about 15% of the planets have been discovered. But interestingly, we're also finding a lot of super-Earths. This is something that doesn't exist in our solar system. These are planets that are about 1.25 to 2 times the diameter or radius of Earth. And we simply don't have anything that size range in our own solar system. But they are apparently very common, okay? These are planets that certainly could maintain an atmosphere. They actually might even have an easier time maintaining an atmosphere. So they're kind of a sweet spot for a terrestrial planet. There are also things that are called mini Neptunes. These are gas giants, but very, very small gas giants. Again, something that we don't have in our solar system, okay? All right, so more data will help us find planets in this shaded region, right? So these would be kind of like perfect Earth analogs in terms of their distance and their size, all right? But they don't have to be perfect Earth analogs. We still find a lot of planets that are in the habitable zone. I'll mention that in just a second, right? But notice that we do tend to find a lot of Earth-like planets that are much closer to their stars. But that's the bias, right? These are much easier to detect with both techniques, the Doppler and the transit method. So we are finding a lot of, Earths, but very close in, okay? So some extrasolar planets have highly elliptical orbits, I mentioned that. Planets show huge diversity in size and density. And some massive planets called hot Jupiters orbit very close to their stars. That was the first one that was discovered. Okay? So summary here, orbital properties such as period, distance, and shape. We can then even get things like mass and size, and then we can get atmospheric properties. All right? We found a wide variety of masses and sizes. All right? And then we found many planets orbiting closer than any planets in our own solar system. But of course, those are easier to find. So keep that in mind. But that is still interesting. There are apparently a lot of very close planets, a lot of tight planets. Sometimes those planets that have very tight orbits around their stars are around stars that are smaller than the sun, which is also interesting because that means that that region isn't so hot and inhospitable as, say, the orbit of Mercury is in our own solar system. Okay? So let's talk about, maybe why we would even find something like a hot Jupiter. Because if you recall the Nebular theory, it proposed that there was a frost line and that planets like Jupiter could only form outside that frost line. That was something I made a big deal about. But now I'm saying there's hot Jupiters that are right next to the stars in the orbit, but that's impossible, right? Because how could you get a Jupiter-like planet, a planet that requires, icy hydrogen compounds to form in the first place, become massive enough to pull in gaseous hydrogen compounds? How could you get that inside the frost line when there's no ice? Because it's melted. You can't. The only thing that can actually be, amalgamated or accreted into a planet are rocks and metals. So Jupiters cannot form close to stars. So there must be another explanation, okay? And there is. There's something called drifting, okay? So the Nebular theory predicts that massive Jupiter-like planets should not form inside the frost line, which is at about 5 astronomical units for stars like our sun, okay? But we see plenty of stars like our sun that have Jupiter planets that are much closer than 5 astronomical units, okay? So this discovery of these hot Jupiters, that's the name given to them, kind of a cool name, right, has forced re-examination of the Nebular theory. Either it's totally wrong and the idea of the frost line just was dead wrong, or something else is happening. So the explanation that astronomers have come up with is that the frost line is still a rule, and these Jupiters did form outside the frost line where there was ice, okay, where there was hydrogen compound ice, including water ice, but then they migrated inward, okay, and they did that through gravitational encounters, okay. Now, why would that not happen in our own solar system? Maybe we just didn't have enough dust in our solar system to cause that to happen. So a young planet's motion can create waves in a planet-forming disk. And we do see this when we look at protoplanetary disks. We see these waves, we see gaps. They're kind of like gaps in Saturn's rings. Models show that matter in these waves can tug on a planet through kind of resonance and gravitational tugs, causing the orbit to gradually migrate inwards to become smaller and smaller, okay? And this is through conservation of energy and angular momentum. Furthermore, close gravitational encounters between two massive planets can inject one planet while flinging the other into a highly elliptical orbit. So this combination of interaction with the planetary disk and the dust, and then maybe having more planets form, could lead to both the existence of hot Jupiters and more ecliptic orbits, or eccentric orbits. So more elliptical and less circular. So that's interesting because actually that means that the two explanations kind of go hand in hand. The fact that we're finding higher eccentricity orbits, so more elliptical orbits, and we're finding hot Jupiters, those could both be explained by solar systems that form with a greater density of dust. Maybe larger dust particles, maybe a less strong solar wind early in the formation of the solar system that didn't blow out as much dust. So perhaps that's the commonality. That's the explanation that tells us why we see a lot of solar systems that are different than ours. Okay? So multiple close encounters with small planetesimals can cause inward migration, and resonance can also contribute. Okay? So this is just asking what happens in a gravitational encounter that allows a planet's orbit to move inward. And the answer here is it transfers energy and angular momentum to another object. Okay? All right? So observations of extrasolar planets have shown that the nebular theory was incomplete, not wrong, but incomplete, and effects like planetary migration and gravitational encounters might be more important than previously thought. Okay? And our solar system just had a little bit less than that than many solar systems have. Okay? All right? And so that's going to, say that, our solar system might be somewhat unusual, but not not incredibly rare. Okay, so as many as 20% of stars may have Earth-like planets in habitable zones. Okay, however, the location of our planets relative to our sun may be rare and explained by an active phase, as I said before, of the sun with fast rotation, resulting in strong solar winds. So it's sort of like our solar system has so many things similar, right? Gas giants, the size of the planets and everything, but it's just a little bit more spread out. The planets didn't migrate as close to the star, and that just might have been a particular situation of our star, maybe the interstellar medium it found itself in, or just the fact that our star went through a very active, strong solar wind phase. And other stars do that too, but ours may definitely be in the minority there. Okay, so in conclusion, the original nebular theory can account for the existence of hot Jupiters, but planetary migration can, and it's ongoing refinement of the theory and explaining how this could happen. All right, and are planetary systems like ours common? We really don't know yet, right? And further study is necessary. Okay, so this was a relatively short chapter with a couple of concise ideas. How do we detect planets around other stars? Doppler effect, transit method. Okay, those are the two primary ways, the ways you need to understand, the ideas behind, and need to remember. And then, how are other solar systems different? Well, they tend to have hot Jupiters, and they tend to have planets closer into their stars, although that could be a measurement bias, but they definitely have more elliptical, higher eccentric orbits as well. Why is that? Probably because most solar systems have more dust in them that lasts for longer, for hundreds of millions of years longer than in our own solar system. Okay? All right. Well, thank you so much for watching this video. I hope it has been interesting and informative.